Welcome to the pre-recording of lecture 90, which is somehow the last lecture in this course. In the next lecture we have a review. And it's still within the last part on applications. The title is on running Newton's method to compute Taylor series, and to do this within the course of supercomputing on graphics processing unit. So in a way, it's not really an application from the point of real, what people might call applications, but it's kind of fitting within the software topic, the connection with building software that scales. So the building blocks that we are using are evaluation and differentiation. That's the first building block. And then there is the linear algebra. By the linearization, we get into a blocked Toeplitz system. So after the overview, I will explain data staging algorithms for evaluation and differentiation. And I will then also, in this last part, indicate how Newton's method for Taylor series is implemented, is accelerated on the with a graphics processing unit. Okay, so here is the general problem. We have a system of polynomials in several variables. The coefficients are truncated power series in one variable. So we have the many variables and the one variable coefficients. If you like, truncated power series is another word for polynomial. And the word polynomial here could also be seen as a truncated power series. So in some sense, we are very precise with our inputs. So there are sequences of monomials, but they actually fit a very, very general pattern, given that any analytic system can be approximated locally by power series expansions that at some point you truncate. So the other part of the input is a vector of truncated power series. So we have several variables. For every variable, we have leading terms in a power series development. So the series that we consider here in this lecture are Taylor series. So there are other series, Laurent series, that begin with negative exponents, and there are then Puiseux series that have fractional exponents. So they are more general and more fitting within the theory of formal power series. Here we deal with Taylor series as in calculus. And also we assume, therefore, that the problems we consider are analytic. So what are now the difficulty? What is the difficulty of things? We have the number of polynomials, the number of variables, the degree of truncation of the series, and then the working precision. So scaling this up, so we can ask what is actually now most expensive in the two stages that you consider, evaluation, differentiation, or is it the linear algebra? Or is it something else? Okay, so here are the questions, the main questions if we are going to consider this problem on a graphics processing unit. How can we fully occupy the GPU? And these are actually thresholds from below. So if you consider parallel computing, supercomputing, you have to pick your problems that are sufficiently large to take fully advantage of the computing that you have at your disposal. Then there are what I mentioned, so the proportionalities. So what is here now actually the bottleneck if you are running Newton's method. Then the higher precision, so this factors into the quality up. So most of the time, if you consider nonlinear problems, so the standard 64-bit double precision may not suffice, and I will motivate that again, then you can ask yourself, for which level of precision can the graphics processing unit compensate for the extra cost overhead caused by multiple double arithmetic? All right, then there is the linearization. Linearization is a very common tool in linear algebra. It struck me when I was in 2016 listening to an invited talk in the International Conference on Linear Algebra Society. So that talk was entirely on linearization. So what is the point? So instead of considering a vector of power series, you consider a power series that has vectors as coefficients. So instead of considering a matrix of power series, you consider a power series where the coefficients are matrices. So in some sense, it's kind of a funny play of words, but from a point of view of computation, it makes a huge difference. So I should say that also computing with power series as they are numbers is perfectly possible. So a power series is invertible if the leading coefficient is a constant and different from zero. So if you can invert the leading coefficient, then you can invert the power series. So in some sense, it's quite tempting to work with templates and overloading and doing your arithmetic with the power series. And in some sense, it's necessary if you go for Laurent series, for example, because then you are forced to work like that if your Jacobian matrix is singular. So that's part of the resolution of singularities. But for Taylor series, you're much better off by linearizing. Because this gives you a nice block Toeplitz matrix. And then actually the linear algebra is then reduced to a lot of matrix vector computations, for which there are standard operations. But it is possible to reduce everything, however, to expression evaluations. So there are two parts in this lecture. So there is the linear algebra perspective, and there is the evaluation of and differentiation of expressions. They can be used both to solve the same problems, but they are using different tools. Okay, so let's look at evaluation and differentiation, but now actually with a twist. So when we are evaluating a monomial, the values where we evaluate are actually power series. So what we are constantly doing is actually polynomial multiplication. And that's also known as convolutions. So convolutions are one of the basic building patterns. So we encountered convolutions earlier with the fast Fourier transform. Here the convolutions are kind of different in the sense that the degree of truncation is not 1024 or higher. It's actually a very small number, relatively speaking. So think about 32, 64 or something like that. So when we have to compute many of those convolutions, the high school algorithm is just perfectly fine. With a twist, however, on a graphics processing unit, you do not want to have thread divergence. So it looks, if we do data parallelism, we have to compute d plus 1 coefficients. So now think d is 31, so you have 32 coefficients, and the kth coefficient, the zk, gets computed by the kth thread. Looks very fine, except that the number of operations that needs to be done by each thread is different. So the number of operations actually depends now on the thread. So you have a lot of thread divergence here. You can make it immediately uniform by doing padding. So you see the index k minus I in the definition of z sub k. You extend the y, you prepend or you insert as many zeros as the degree. So at the expense of extra shared memory, you can avoid thread divergence, and the multiplication of two power series can be done in linear time, linear in the truncation degree. Here is the pseudocode now for the convolution kernel. And this convolution kernel is defined for various levels of precision. So that's really the basic block. The data gets loaded into shared memory arrays, and then you see the instructions that every thread goes through. So there is the first two instructions are the definition of the x and the y. So you have the kth thread that loads in the kth element of x, that initializes the zeros at the kth position of y, and then also loads in from the global memory into shared memory the kth component of the second input vector. So these instructions are the instructions that are executed by the basic building block to do one convolution operator, and that is typically done by one block of threads. Okay, now how is this used? So we are evaluating and differentiating one monomial. We are doing many monomials, but then at the second layer we are evaluating. So, and this can be done also very efficiently by using algorithmic differentiation. So if you look at this monomial, we have 5 multiplications, and these 5 multiplications are accumulated in what is called the forward product. So the last component of the gradient vector, the last forward problem is the value, and the next to last product is actually already the last component of the gradient vector. So the observation of algorithmic differentiation is that when you evaluate, you actually, with some additional work, you can also obtain the entire gradient vector efficiently. So you see 3 columns. So the second column is the backward, are the backward products, and then you have the cross products. So even if you're not doing parallel computation, organizing the computations in that manner can save you significant amount of time compared to the plain high school algorithm to evaluate product with many variables. So in high school people never do that, so that's why people don't teach those algorithms. But instead of having an n-square algorithm, you have a linear algorithm in the cost. And with parallelism, so the main statement is at the bottom here. If you have sufficiently many blocks of threads, so if you fully occupy your GPU, then it actually only takes n steps. So the cost to evaluate and differentiate one monomial is proportional to the number of variables. It's not quadratic at all. So you have a huge reduction step already there. And remember, we also have the reduction step from the convolutions. So the convolutions actually, when they're done by one block of thread, it's like you're doing them on a number. So the overhead that we experience from the convolutions from working with the power series can actually already absorbed by the GPU acceleration. All right, so here is then putting things together. I explained this also with an example. So in some sense, if you look at the evaluation of a polynomial, it looks like a very sequential process. And especially if you would like to be very frugal with your computations. But here in my sparse example, I don't have the saving, or you could say, look, I'm in the first monomial, I'm multiplying x1 with x6, and x1 times x6 comes again in the second monomial. So in a way, thinking about trying to do an optimized evaluation where you really do not want to try to organize it in a way that minimizes absolutely the number of operations is here counterproductive. It will lead to optimized code for, say, a very particular case, but it will be very difficult. It will impose all kinds of barriers. Instead, we take the monomial by monomial view, which allows for a very high level of parallelism. So you see now that these convolutions can be organized in a way such that the monomial with the largest number of variables is going to determine the bottleneck. So in some sense, the arrangement of the monomials for this example here is a little bit similar to the task graph that we have seen. So you can see that the number of lines actually gives you a theoretical bound on the maximum amount of parallelism that you can get. It fits the scalable model of GPUs very well. I'm just assuming all the time that I can give my GPU sufficient many jobs to do. One needs to be very careful how to define the jobs. So in here is where the staging of the data is very critical. So the power series coefficients are stored in a way that is outlined here in one very, very long array. And we have the coefficients. So the A naught here is actually a sequence of 32 coefficients if your degree of truncation is 31. So we have the input coefficients, we have the input power series where you want to evaluate your polynomial. We have the forward products, the backward products, and then the cross products. So we have this very long array, and we have stored the beginning positions of each block. So a convolution job is then actually defined by indices in this array A. And I actually explain it here for one array, but if you have a complex array, you would actually have two arrays, one for the real parts, one for the imaginary parts. For the multiple double numbers, if we are working with octo double or deca doubles, tenfold precision, we have 20 arrays. So this model scales very well and allows for very efficient memory coalescing. It is also a good programming model in the sense that you can define a convolution job at a very high level. So the kernels can just take into sequences of indices or three indices for the input and the output. So they are just running the convolution jobs. So that's another mistake that one often makes when one does the GPU acceleration. One has to think about instruction level parallelism. So one breaks it down to the elementary level of convolutions. And the convolution jobs are doing this. So here are the convolution jobs. And again, the main result is that what I announced already, that the largest number of variables in one monomial is going to determine how many layers one needs, how many convolution layers one needs. I should say what I actually sweep under the rug now are powers. So all my monomials were mapped into products. What do you do when you have, say, x to the power 5, x1 to the power 5? Well, you can hide it in the coefficients. So you can pre-compute these powers in the coefficients. So, and this could also be arranged efficiently with lookup tables that are pre-computed. They are special case here. And you can also always rewrite your polynomials so that with extra variables that everything actually is a product of monomials. That's another approach. All right, any convolution job is then defined by this triplet of the input locations and then the output locations in the data arrays. Addition jobs are done as well in this way. So we've seen the tree-based algorithms for the addition jobs. Well, here the addition jobs are additions, updates, essentially of the convolution job. So the tree summation algorithm is running on blocks of threads. So there is also here no thread divergence here. So the tree algorithm depends then on the number of monomials, and the nice thing is that if you have even many monomials, the two logarithm will actually quickly reduce this. So if you have 1000 monomials, it will take 10 steps to reduce everything. Again, given sufficiently many blocks of threads, we actually now have very nice bounds on the optimal speed up that can be obtained. So on the optimal number of steps that it will take. So the speed up, so if you would look at this, so you would actually have this factor d times n. So I'm assuming here that all the convolutions, they are actually absorbed by the sufficient many parallelism. So doing a convolution with a block of threads is just like doing the evaluation, as it were, with numbers. The reduction then is then, so for n larger, much larger than n, I will give examples, then actually you have this d times n over logarithm of n. All right, I have many GPUs, so my computers have lasted quite some time. So the first GPU is more than 10 years old. Compute capability too. This has some advantages. You have portability over several generations of GPUs, but of course I'm very well aware of the tensor cores capabilities in Volta, which are actually now here not exploited. Nevertheless, if you consider the peak theoretical performance, so we will actually realize we will be able to scale our problems so that teraflop performance is obtained. So for sufficiently large problems, we can actually realize very good speed ups and very good performance. Comparing GPUs has the advantage that you don't have to get into the rather unfair comparison with the CPUs. Okay, so here are the test occasions. I considered polynomials which consisted of relatively few variables. So we have the total number of variables, but then a relatively small number of variables per monomials. So we have the little m and the little m. Then there is the total number of polynomials, and actually what is determining, so we have polynomials of very different shapes. So polynomials that have very few variables, but many terms, and then polynomials that have relatively few terms. So this is this P2, but we have actually many variables. So the nonlinearity of the polynomial. So the last type of polynomial is actually you have a sum of quadratics. So you have essentially the little m is 2. So every monomial is a quadratic monomial, but you have 8,000 of them. So in generating these test cases, so you can do this completely synthetically. So the number of convolutions and the number of addition jobs is pre-computed. So it's a good indication that the number of convolution jobs is in the 10,000s. So this was already say something that actually the shape of the polynomial should actually not matter that much as long as you have sufficiently many convolutions and addition jobs. Okay, so then here is the performance. You can kind of see the evolution of the speed of the GPUs. So Volta is my most recent one, purchased in 2019. The C2050 was purchased, I think, 2012. So you can see that Moore's law, in the sense that from the consumer perspective, that computers, Moore's law says something about the size of the transistors, but what you actually like is that computers double in speed every year or every other year. And that actually, with the progress that the GPUs have made, you see a 20-fold improvement. So care was being made for the additions, and here is also actually the big point. The convolutions are actually being most absorbing here. The tree-based algorithm for the additions is good, but additions are linear. So in some sense, you just have to do them, but they are actually really insignificant. All right, then the problems were also kind of generated is that you can kind of, I tailored this for the Pascal GPU, which evaluates a polynomial in about a little more than 1 second. So you can count all the number of multiplications that you do, the operations that you do, and then you see that in double precision, so if the precision is done by a factor of 10, so instead of precision 16 decimal places, you have about 160 decimal places of accuracy. Then you see that you can realize not theoretical, in practice, we observe a 1.52 teraflop performance. Scalability, so we can scale the doubling of the precision and keeping the degree fixed of the truncation degree, or we can double the degrees. So the point of this is that as you scale up enough, at some point, precision and degrees, the problem becomes more and more compute bound. And this should also be obvious in the log2 plot. So the shape of the polynomial matters actually when you work with doubles. It does not matter that much anymore at higher precision. So doubling the precision each time, and you observe that the bars, actually the height of the bars, becomes quite close to each other. All right, half an hour in, I probably will spend too much time on this. Also observe if you double the size of the problem, these are 2 log plots, you would expect actually a quadrupling. So because the algorithms are quadratic in the degree of truncation, but actually it's almost linear. So the height of the bars, especially for decadouble and for octodouble, the difference between the bars, if you double the degrees, then actually it's not that bad. Okay, so that was first half hour. Now we have the running of the Newton's method and the solving of a triangular block Toeplitz system. So the QR is actually there, the bottleneck, except that it is actually not, because the QR is going to be applied only on the leading coefficients. So once you have the leading block done, if that is accurate enough, you don't have to run QR anymore. So we treated QR in multiple double precision with the householder methods in a separate lecture. And that was an interesting computation. It's cubic. But here actually in the application, the activity will be much more in updating the matrices. So there will be a lot of matrix vector multiplications. So this is here for series truncated after the 4th term. And you can see also the task graph. If you would consider the highest level of parallelism, so you would do a multi-core algorithm, then you would organize it in this fashion. But actually, in the GPU accelerated world, it's actually not done like this. But the kernel launches are still organized like this. So you will launch the kernels to update the right-hand sides. And there should be sufficient, so the dimension should be sufficiently large, because in the last step you only have one matrix vector multiplication. So the size of your matrices should be sufficiently large to keep your GPU fully occupied. Okay. Here is a sideway, so what turns out to be kind of not entirely unexpected, but the size of the numbers, actually, even if you work with multiple double precision arithmetic, you have to be careful with overflow, because the exponents in multiple double arithmetic are limited to the 11 bits of the 64-bit numbers that you have. So here are the data that are generated. So I work with modified exponentials. So we do not really want that for every variable we have the same series. So there is this scaling parameter alpha that allows to differentiate a little bit. For the complex arithmetic, you take numbers on the complex unit circle. Here is a motivation then. So this comes from numerical analytic continuation. So the leading coefficients and power series approximations need to be computed more accurately than the later terms. So I sidestep here a little bit the question, how many terms do you really need? It turns out that if you know extrapolation algorithms, that number d can be sufficiently reduced, although the more the better. So I went up to octodouble, so double, so starting from double, quad double, octodouble. So we think quadratic convergence. So that's also the reason. You could always, of course, run it on numbers as much as you like, but it's not good to see not a number appearing all the time. So, okay, monomial homotopies. You can also ask, but wait, these are actually, should have warned you, this is not at all an application then. Well, if you go to 2 columns or many columns of monomials, then actually you have general polynomial systems. And the question that we asked earlier, what is actually now the bottleneck? Is it monomial evaluation of differentiation? Or is it the linear algebra? The dimensions, well, you should actually go to 1024. So this is when a GPU is really critical here. For smaller dimensions, you cannot fully occupy your GPU, and also unless you then do it in batch. So with nonlinear problems, you have many more solutions, but then you have the batch processing, the filling up of the GPU, and we covered streams last time. Okay, here are the different kernels, the kernels for convolutions, the householder QR, which breaks up into many different kernels, but we don't use this fine breakup here in this lecture, so that was another lecture. You have the updates. So you store the Q and the R, and typically for convergence, so running many times QR is, you can do that, that's useful, but I only will do one QR step. You assume that actually when you go from double to double precision, your first leading coefficient is already almost accurate, and then you compute the other significant part. So you use multiple doubles in this staggered precision way. Again, reminding our matrices are initially very well conditioned. We are working with Taylor series. Residual computations. This is still research code. You want to have something to check your convergence. There is also the updates that you check, the forward error. So when we run Newton's method, we update the solutions. The magnitude of the updates, so the delta x, is a measure for the forward error. The backward error are also called the residuals. Okay, so you have stop criteria, when to stop the sequence. And here is one result. So here is the pi. We have the evaluation of the differentiation, which occupies almost 30%. The residuals are actually computed up to full precision. So that turned out to be also 30%. Now, I must say that you can simplify there. Instead of doing the entire residual for all equations, you could pick a random equation. So you can significantly reduce the residuals there. What you can't really reduce are the updates. So this will then come a lot more dominant. Notice that the QR, we only do this once. It's still a significant part, but it's actually certainly far from dominant. And actually the back substitutions, the BS actually comes almost, because you have to do the back substitution still many times. This actually still becomes significant. And that was even an earlier lecture, solving triangular systems. There actually you know that you will have to go to larger dimensions to observe teraflop performance. So 1024, even in octo double precision for back substitution, is not sufficiently large computationally seen then to achieve full teraflop performance. Here is the good news. If your systems become more and more general, so you go to 2 columns now, then you see that convolutions are at 44%. And this is the good news, because actually the convolutions are something that can be worked out in a very fine-grained parallelism. And for that, actually, we can occupy our GPU very well with the convolution jobs. And the fact that that gets more and more dominant as the size of the system grows is very promising. Okay, Uh, Nice thing here, if you double the precision, the problem becomes more and more compute bound, and the GPU can absorb the extra cost overhead. So that's actually, for the application perspective, the most significant part. So in going from double double to quad double, you can see that the wall clock time, so the red bar is actually the bar that you should look at. And actually this goes for all precisions. From double to double double, you have only, it's a two-log plot again, you only have one increment in the bar. So you go from 8 to 9 to the from the leftmost bars. And you see that the blue bars are increasing. So that actually means that the GPU gets more and more busy. And when it gets to 8 octo double, then you see that the problem is fully compute bound, and actually the GPU is responsible for most of the work. Okay, how large a degree do you actually really need? That's a very interesting mathematical question. And again, if you know extrapolation algorithms, that degree should not be 40. But if you look at it from the other perspective, for the convolutions, we actually want large degrees. Then with 40 degree 40, we actually have teraflop performance on Volta in octo-double precision. So from the perspective, you want to keep your GPU busy, have high degrees, certainly. But from a perspective, from a more mathematical perspective, it might make sense to have blocks of threads collaborating on many different convolutions. So here the granularity of the convolution jobs was designed such that the degree would be sufficiently large to occupy blocks. If you are using good extrapolation algorithms, this might not be necessary. Okay, I thought I would run over time, but I don't. So this is preliminary, but also published. So there are 3 papers, 2 published, 1 under review, which describe this type of application using graphics processing units to compensate for the cost overhead of working with Taylor series. So even if you are not into multiple double arithmetic, or if you want to consider only double doubles, then the cost overhead from Taylor series is still considerable. And you also have the scaling up of the precision, which is also another motivation. So even if you wouldn't be working with Taylor series, then going for GPU acceleration to compensate for the cost overhead of multiple double arithmetic is certainly worthwhile doing. Okay, I hope that this last lecture was interesting. So thank you for your interest in this work.